Welcome to lesson 7, the derivative as a function. So in this lesson, we're going to build on what we did in lesson 6, where we defined the derivative as a limit, and we defined it at a point. So a point like x equals a. And actually, what we realize in this lesson is that the derivative itself is also going to be a function. And so we're going to talk a little bit about the derivative as a function and think about kind of what its shape is and how its shape is related to the shape of the original function. So you can see we're going to do things along those lines, calculate the limit of the limit definition of the derivative for just any value of x, not just a given value of x, sketch its graph, and then talk about places where a function would not be able to take a derivative, which would be non-differentiable points, and a few other things. So we're going to go ahead and start by just filling out that definition of the derivative as a function. So the derivative function f prime of x, same notation obviously, is the rate of change. So we said in the last lesson that it's the instantaneous rate of change. So we're just going to kind of shorten that is the rate of change of f of x at x, and is given by that same limit that we've already done. But in this case, oops, let me put a derivative notation in front of that. So f prime of x is equal to the limit as h approaches 0. And we just don't have an a in this situation since we're doing it at a general x. So we just really replace what used to be an a with an x when this limit exists. And so then we're just going to add an extra definition of the word differentiable. So f of x, the original function, is differentiable at every x value for which this limit exists. So differentiable is basically just a way of saying I can take the derivative of this. The limit does exist, the derivative limit. So non-differentiable would be the opposite of that. I cannot take the derivative at this of this function or at this point because that limit does not exist. So we have some alternate notation. F of x is the common notation, but f prime x, we could write it as y prime. Or there is this secondary notation dy dx. And that comes from the fact that there were two different people who developed calculus at the same time. And one of them used this prime notation and another one used this dy dx. So we're going to use these two things interchangeably. It just means exactly the same thing. Every once in a while, you might see d dx, like the derivative with respect to x, and then potentially, of whatever that function might be. And of course, we have that alternate limit. This one is still requires you to have an a value, right? So this isn't necessarily giving you this alternate limit. It's still just going to give you f prime of a. So it's at a point as opposed to the entire function. Okay, so in the next example, or two examples, we're basically going to use this same limit, but we're going to do the derivative at for general not at a specific point. So we're gonna use the limit in terms of x without the a. So we'll start with this function here. F of x is 1 minus x over 2 plus x. And f prime of x will equal the limit as h approaches 0 of f of x plus h minus f of x all over h. So in that first step, keep in mind what you're doing. You are going to be substituting x plus h into this function. So everywhere you see an x, you need to replace it with x plus h. So that would be 1 minus x plus h. You notice I have parentheses, 2 plus x plus h, because I have to subtract this entire input, which in this situation on the top has 2 terms. Minus f of x. Well, f of x is just this equation. F of x equals this thing here. So 1 minus x over 2 plus x. And that whole thing is over h. So you might recall me saying in a video from lesson 6 that you have to be able to deal with complex fractions in these problems. You have to be able to simplify this. Again, there's more than one way to do it. I find one of the most effective techniques is I'm going to multiply the top and bottom by the common denominator of all of the denominators in this problem. So in this problem, I have a 2 plus x plus h and a 2 plus x. So I am going to use the product of those as my common denominator. Whatever I multiply on top, I have to multiply by the same thing on the bottom so that the entire expression does not change value because I've just multiplied it by a 1. Okay, so that gives me the limit as h approaches 0. Now, when I multiply this by this first term, the 2 plus x plus h's will cancel. So I will have my numerator times 2 plus x. So I'll call that 1 minus x minus h, just distributing the negative there, times 2 plus x. Then I have a minus in between. And when this whole thing gets multiplied by this, the 2 plus x's cancel. So I'll have 1 minus x times 2 plus x plus h. So that is my new numerator after multiplying that out. And again, the advice I would give you, strongly advise, leave the denominator just written in that factored form, because eventually you're going to want to try to factor and cancel. So the denominator is already factored for you. All right, so we got through the tough part of the complex fraction. Our next step is going to be to simplify. We're going to multiply all this out, distribute this negative, combine any like terms we can. So again, I'm going to just skip ahead and show the work of doing that. So you should probably take a moment to hit pause so that you can do that work yourself and then compare your results with mine. All right, so I multiplied everything out here. Then I left the subtract in front of the parentheses, multiplied everything out here, and then just worked on canceling. If I have a negative 2x minus a negative 2x, those are going to cancel. So basically everything here that is matched here will cancel out. That left me with just, oh, sorry, I didn't get the 2's. Those cancel too. So that left me with just negative 2h minus h, so negative 3h on top. This stuff's still just hanging out on the bottom. The h's cancel, and then I'm going to plug in my h equals 0. So here is my final answer for the derivative function. But the next one is pretty much the same idea. It's just that now I'm giving you a position function, and you're supposed to find the velocity function. As we studied in lesson 6, velocity is the derivative of position. So give it a try, same process. Want you to pause the video and see what you can make. using the given s function to find the derivative, which is the velocity function. All right, so I have applied my limit to the position function, which should give me velocity. I plug the t plus h in first here. Then I subtract and just take s of t, which is here. And notice immediately my constants cancel. And then I'm going to multiply this all out here. Minus the minus 16t squared. So now my 16t squareds cancel. I notice I have an h in both terms in the numerator, so I'm going to factor that out. Left with, which cancels with the denominator, left with this expression here. And when I plug in h equals 0, this part will go to 0 and I'll be left with just negative 32t for my velocity. Okay, so those are two examples of just finding the derivative at a general point, a general x, a general t, not at a specific x equals 4. It's really the same limit. And quite honestly, at this point, if you were asked to find the derivative at a point, you could do this same process generally, find the equation, and then plug the point in at the end. All right, so we have one other type of thing that we're going to do with this derivative function, and that is try to get a sense of what it looks like. If we're given a graph of a function, what does the graph of its derivative look like? And so the directions here say use the graph to approximate values of the derivative at various points. And then we're going to try to plot that over here. So this is my graph of f. And over here, we're going to graph f prime. So how are we going to do this? How do we approximate the value of f prime? Well, we've talked about, especially if we're looking at a graph, one interpretation of the derivative, it's the slope of the tangent line at that point. And we can even really call it the slope of the curve, right? So what I'm going to do is I'm going to come into some places, like maybe I'll pick, well, not with my highlighter, I'm not. Maybe I'll pick this x value right here, which is negative 1, 2, 3, 4. So 1, 2, 3, 4. That would correspond to this spot here on the derivative graph. And I'm going to try to draw in just a little bit of that tangent line. And I'm going to estimate about what that slope is. Now, of course, if you drew it, you know, we're just eyeballing it. If we drew it a little bit more, you might be able to see an actual, you know, rise over run. And it's positive, it's uphill, and it's pretty steep. So maybe its slope is about 4. Could be. So that means over here on the derivative, when x equals negative 4, the derivative value will be 4-ish. We're just approximating. Okay, I'm going to erase that extra little bit because if it goes too far, it makes it a little hard for me to draw more. So this point, I'll get back to at the very top of the hill here of the f of x function is an important point because its tangent line is going to be horizontal there. It will be horizontal at the top of the hill or at the bottom of a valley, right? And so what kind of slope do horizontal lines have? 0 slope. So I have two x values. Of course, neither of them are perfectly lined up at a whole number value, but I can approximate where they are, where when I go to graph them in my derivative, the derivative will be equal to 0. It'll be an x-intercept. So let's see. 1, 2, maybe like 2.8 or something negative, sorry, 2.8. So I'm going to draw a dot on my derivative graph where the derivative is 0 at negative 2.8, x equals. And if I look at the other one over here, it's like a little bit more than a half. So I'm going to come over here to a little bit more than a half, and it's also going to be a place where my derivative is 0. So if I'm just going to log these down, at negative 4, we approximated it to be 4. At negative oh, sorry, negative, what, 0.8? No, 2 point something, negative 2.8. Negative 2.8, we found it to be 0. At maybe 0.7, we found it to be 0. So let's pick a couple more points, maybe somewhere in here, like at x equals -1. If we try to draw that tangent line in, it is downhill now, so its slope will be negative. It's not as steep as the one we had over here at -4. It's definitely less steep, and if I were to kind of draw that line out, I'm going to approximate that to be like a -2, a slope of -2. So if x is -1, I'm approximating my derivative to be -2, and I've filled that in over on my derivative graph. And let's do one more somewhere over on the other side here. We could even take the x equals 2. X equals 2. And again, we're trying to approximate. Sorry, that wasn't the greatest picture there. That wasn't any better. Straight line. I'm having a little trouble getting it in quite the right place, but you get the idea. Now, again, it's positive, so it's going to be uphill. It looks like it's almost as steep as that. Maybe not quite. I mean, again, we're just approximating, so it doesn't have to be perfect. Maybe it was like 3.5 or something like that. So I'm going to go over to my derivative graph at 2, 1, 2, 3.5-ish. So if I'm going to try to draw this picture, and I don't know for sure that I got the lowest point there. Perhaps it went lower somewhere else, but I can see a shape coming out, and that's the general idea of what we were trying to do at this point. So this would be a picture of my derivative, and we did that based on just looking at slopes of tangent lines at different points on this function. You can also think of it as the slope of the curve. Sometimes I think the tangent line is a little bit easier to visualize. So I have, I believe, a place where we're going to fill in a couple of observations. So I want you to take a minute and look at these observations and go back to the picture that we have on this page and see if you can get a little bit of intuition about when is the derivative 0? What about uphill tangent lines? When are those happening? What can you say about the function itself? Or downhill tangent lines? What's the function doing when the tangent lines are downhill? Okay. So take a minute to think about that, press pause, and then I'm going to go back and talk through them. Okay, so the first one asked us about when was the derivative equal to 0? Here's where the derivative is 0. It has x-intercepts. And we discussed that as we were doing this process, it's going to be where the function itself has a horizontal tangent line. And that happened at the top of the hill, the bottom of the valley. Okay, so we can fill that in. Where the tangent line to f of x is horizontal. And we'll fill in exactly where that was happening. Okay, and then if we think about uphill tangent lines, we'd had 2 places in our picture. All of this area here is going to have an uphill tangent line. These are going to be downhill tangent lines. And then uphill. What do you notice in the 2 uphill areas? What is this function doing? It's increasing, right? It's getting bigger. As you move from left to right, this function is increasing. in both of the places where it has uphill tangent lines. And what about where it has downhill tangent lines? What is it doing in that area? It's decreasing, again, left to right, because if you go right to left, anything that's decreasing would suddenly become increasing. So we're always looking left to right. Now it's decreasing in this area. So we could fill in both of these as well. Uphill tangent lines occur when f of x is increasing. And what that basically means, one way of kind of interpreting that, is f prime of x will be positive because uphill tangent lines have what kinds of slopes? Positive slopes. So the derivative will be positive when f of x is increasing. Okay. And we're just going to flip-flop that for downhill tangent lines. Downhill tangent lines occurred when f of x is decreasing. Downhill tangent lines, lines that go downhill have what kind of slopes? Negative slopes. So the derivative will be negative when the function itself is decreasing. So when we're talking about a derivative being positive, that means that it's only going to be able to be graphed in quadrants 1 or 2 because the y values, the derivative output values, have to be positive. Whereas in the next one, when we were talking about the derivative being negative, that means in that part, that x value, we're looking at graphs that have to be down in the quadrants 3 or 4. So if we go back and take a peek, where my function was increasing, my derivative was above the x-axis. It was positive. Increasing, positive. Where my function was decreasing, my derivative was negative. It was below the x-axis. That's kind of a intuitive piece that I'm trying to point out here so that it makes it easier for you to continue to work on these kinds of problems. And finally, the steeper the graph, the larger the magnitude of the derivative is. In other words, it's going to be a bigger number, not counting for negative. So it's almost like the absolute value of it, right? That's the magnitude is larger for steeper f values. Okay, so those are the observations that we got from just doing this process once. And I have 2 more pictures here. And I'd like you, again, to pause the video. You'll notice I'm not asking you to be totally precise, but I just want you to get an idea. Try to figure out about what the shape of each one of these derivatives would be. And if you draw it curved and it's actually straight, but it's all generally in the right place, that's fine. Or if you draw it straight and it's actually curved, but everything is generally in the right place, you're in good shape. So go ahead and pause, give it a try, and then I will talk through them as well. Okay, so if I'm kind of using the observations we came up with in the last box, I started by figuring out where is this first one have a derivative that's 0? Because then I can mark that directly on my graph, and then I'll look at what's happening on either side. So it has this bottom of the valley at x equals 3, so its derivative will be 0. And on the left side of 3, the function is decreasing, so the derivative should be negative. And in terms of the trend, what is it doing? It's definitely steeper further away from 3, and as I get closer to 3, it starts to flatten out, get closer to 0. So I have indicated that here. Now maybe you used a curve, and that would have been fine. But if you have the trend of more negative, further from 3, and getting closer to 0 as you get closer to 3, that's what we're looking for. And then pretty much the opposite is happening on the other side of 3. We see that these lines are, the function is increasing, so it's going to be positive. It starts out not very steep on this side of 3, but continues to get steeper and steeper. And so again, I indicated that here with a straight line. Maybe yours was curved, and that's okay if it's got that trend of what's happening. The second one is a little bit more challenging. So first, let's note that this function is always increasing, and it's only defined for positive x's. So that means in my derivative function, I'm only going to be in positive x's, and since the function is always increasing, then we are looking at it going to be always positive. Okay, so it's definitely going to only be in the first quadrant. So now what you want to think about is, what's the trend? Are they steep? Are they not steep? Are they getting steeper, less steep? That's kind of what you want to think about. So right at 0, it's really hard. Let me get rid of what I have there right now, to see what's happening right at 0. But very close to 0, the lines are definitely steep and getting less steep. So that is why I have my curve, my derivative curve coming lower. And then it does appear that this graph is going to kind of very slowly flatten out. So, sure, it maybe isn't that it's getting this close to 0 this quickly. I mean, maybe it's more kind of like this, and that's again fine. The idea is the general trend. And then the thing is when I get close to 0, it's really like I almost want my tangent line to be vertical at 0. But what kind of slope does a vertical line have? It's infinite, right? And so that's why what we're indicating is that I'm getting closer and I'm getting bigger and bigger positive slopes as I get closer to 0. But there really isn't a good value at x equals 0, because that's where that thing ends, and it's either going to be a vertical line, or we're not going to be able to draw a tangent line exactly at that point because it's that end point.